So we're here at the iZone, and hi. So who are you?
Hi, I'm Praneeth. I'm a graduate student at UNC Chapel Hill,
So this is the university in
North Carolina,
North Carolina, and what are you
at
showing
Chapel
here?
Hill. So this is a variable focus augmented reality display. So
Variable focus.
yeah. So the current day available augmented reality displays like Microsoft HoloLens or Meta, or even the current day Magic Leap, they all show virtual imagery, but they all are snapped to a specific depth plane, and that causes a lot of discomfort in viewing virtual
What does
imagery.
this do when you open and then close it?
So this is a variable focus single optic AR display. So you can see that there's a deformable mirror membrane which is changing its shape, and the change in shape is coming from air pressure.
This is air.
Yeah. So there's a flat surface, there's a membrane, and then the shape is changed based on the air pressure, and each curvature corresponds to a specific depth for virtual imagery in the
So
real
it's
world.
very important to have variable focus, because when you do AR, you want to focus here or there or what?
Yeah,
You want to see things different places in the field.
right. So there's something called accommodation and divergence conflict that is basically arising from virtual imagery snapped to a specific depth plane, and so you'd have to roll your eyes like that to fuse the images. And especially that's a very big problem in AR displays, because say you want to focus at 3 meters, but all the virtual imagery are snapped to 1 meter, and so you cannot focus both real and virtual imagery at the same time. So it's important that virtual imagery appear at different spatially registered depths, and so variable focus becomes very important.
Did you see the keynote?
I've been hearing about.
This guy, right?
I've
He was
been
saying he's trying to do something called VR, right?
right.
Are you doing for AR?
So I'd say VR, in some sense, it's easy because you're not looking at real world. So it's like completely blanking real world, and then you're sort of okay with doing anything in the rendered, in the totally virtual world. But when it comes to AR, it becomes important that you also have a unapproved view for real world.
And what is the demo right here?
It's the same demo as you can see in the video. It's an automatic implementation of this static prototype. So there are a bunch of electronics that is controlling the air pressure, and then there's a rendering pipeline that renders according to the set curvature of the membranes.
And these membranes and the effect and the quality of the optics and everything, how does it compare? Is it good enough? Like everything will be possible with this, or?
Oh yeah, it's currently in the prototype or a proof of concept stage, but it's not very far from being into a real product, I'd say. Yeah, we currently hit something like theoretically 12 to 15 cycles per degree with the current available LCDs, but this could go as high as 30 cycles per degree with using correct light engines, and I'd say it's not very far from reality.
So right now it's working. It's active. This one.
This one's not active. Unfortunately, while shipping, we broke our Arduino board and we're working with it.
So will you need to have eye tracking or something like that to make it the final product, or?
Oh yeah, this definitely would need eye tracking, because you would want to set the virtual image depth based on where you're looking, and so that should definitely come from binocular eye tracking.
And what you're showing right here with this air, is it possible that it can be fast enough that it can be usable?
Oh sure. So we're currently working on a version which uses very fast linear actuators to quickly change the air pressure, and that could go something like 500 millimeters per millisecond kind of
So if
actuators.
some kind of billion-dollar company comes over here and says, here is $1 billion, can make it work in like 6 months, is possible, or impossible?
6 months probably would be like a very hard target, especially to shrink down the form factor.
People will buy.
Yeah, but probably in a year it shouldn't be very far from reality.
A year.
A year, I think.
Are you going to do it?
Sure.
What's next for you?
So there are a couple of other things which we are trying to target. Currently, the membrane shape is it's a uniform thickness membrane, So the shape of membrane is not locally controllable. So we're working on a version where we can, hit locally controlled target shapes of the membrane, and a couple of other problems related to these things.
All right, make things smaller, more compact, or
Make things more compact in a very good head-mounted form factor, not actuators sticking out, and so the aim of all these people as a community is to shrink these AR displays to form factor of eyeglass.
you want your glasses to have this stuff?
Yes,
How
and
about,
so
what is this PCB here?
It's a display. So this display is reflected off of the membrane, and that is relayed into your eyes. So the virtual image which you see is actually coming from this display. So the effectiveness of the resolution of the overall display is basically dependent on what kind of display we're using. So the higher the display resolution is, the better your images would be.
How big is your team? You have some other...
We have a huge collaboration. We were collaborating with NVIDIA, we were collaborating with Saarland and MPI, and of course UNC Chapel Hill.
How many students?
So currently we are a team of 4 students, 3 postdocs, and 3 professors.
Which one are you?
Sorry? Oh, I'm a student. I'm a graduate student.
So how long time are you going to be studying this? How long does it take?
So it's part of a PhD dissertation. I'd probably show David.
Yeah.
David Dunn is a PhD student whose PhD dissertation is this primarily.
All right. So did he get the PhD with this?
Oh yeah, he's going to graduate probably next year.
Cool. And you?
I just finished my second year. I'm going to graduate maybe in 2 or 3 years.